All right, part 2 of the solutions for this midterm assessment thing. Number 13, the radius of a circle is increasing. At a certain instant, the rate of increase. So these rates, radius of a circle increasing, what is this? This is related rates. In the area of the circle is numerically equal to twice the rate of increase in its circumference. What's the radius of the circle at that instant? Well, let's see what we can do here. We're talking about the radius of a circle is increasing, and then area. Okay, so I'm going to write the equation for the area of a circle. And then I'm going to take the time derivative of that like we do with related rates problems. So dA dt is equal to 2 pi r dr dt. Okay, so now what do I do with that? At a certain instant, the rate of increase of the area, that's this, is numerically equal to twice the rate of increase in its circumference. Okay, so there's something about the circumference here. So let's see, C is equal to 2 pi r. That's the circumference of a circle. And so if I took the time derivative of that, that's just a constant 2 pi times dr dt. Excuse me. So notice here that the time derivative of the circumference is equal to 2 pi times the derivative of the radius. I actually have that here. 2 pi times the derivative of the radius. That is the derivative of the circumference. So since they're talking about area and circumference rates, I'm going to substitute out so the r is left behind, but then the rest of this 2 pi dr dt, that's equal to dc dt. Okay. So back to our info now. The rate of increase in the area of the circle is twice as much as the area of the circumference. So let's say they were just like 2 and 1. They're in a ratio of 2 to 1. So if this was 2 and this was 1, or if this was 4 and 2, or whatever and whatever, that's you're going to divide that over and you're going to get the radius as 2. If you're thinking to yourself, boy, that's tricky, wouldn't have thought to do that. I agree, that's pretty tricky, related rates problem. But sometimes you get a tricky problem. Graph of the even function y equals f of x. Even just means it has y-axis symmetry. If you fold it over that axis there, consists of 4 line segments as shown above. Which of the following statements about f is false? All right, let's see. The limit as x approaches 0 of f of x, that's 0, minus f of 0 is just 0, is 0. That's true. And we're looking for something that's false. Okay? The limit as x approaches 0 of f of x minus f of 0 over x. So what this should make you think of, so f of x, that's as x approaches 0, that's going to be some point around here, some x value that's getting closer to 0, and this is that slope formula, f of x minus f of 0 for x minus 0 equals 0. And the problem here with this function is, on one side, as you approach 0 on one side, you're going to get a slope of -1, and as you approach 0 on the other side, you're going to get a slope of +1. So if you don't say which side is which, then this limit does not exist. So this is false. What about this? What if you do, these all look like slope kind of calculations here, right? So what if you take a point at x, and then another point f of -x, and that's on the other side, and then you divide by 2x. Well, because it's even, and it has that symmetry, the slope, when you take one point and the other one here, it's always going to be 0. That's always going to be horizontal. And then how about as x approaches 2, The slope there, yeah, it's the same on both sides, so that's fine. And then at 3, same problem here, but this is just correct. Here they said it was equal to 0. So that's a sharp corner. You get different slopes on the two different sides of 3. So our answer is B. All right, x's and y's mixed together. That looks like implicit differentiation. So let's do that. This is a product. So derivative of the first times the second minus derivative of 3x is just 3. Derivative of y cubed is 3y squared dy dx. And derivative of that is 0. Okay, I could go ahead and solve this for dy dx, but I actually only want to know the derivative here at this point. So either way, let's go ahead and solve for dy dx. It's probably good practice. So get all the pieces with dy dx's on one side minus move the 3 to the other side. All right. And then factor the dy dx out, which is going to leave 2x minus 3y, which I'm going to then divide. 3y cubed, that is. Okay, and then I'm going to plug in -1 for x. So that gives me 3 over -1 for x, -2. And then a 2 here. 2 cubed is, I'm not liking what I'm going to get here. Feeling like this is not going to be any of these answers. All right, well, let me see what happens here, and then we can check. 2 cubed is 8. Oh, because that's supposed to be 2 squared, that's why. Oh, hold on. Yes, that's my mistake. That should be squared. Sorry, you're probably jumping up and down in your chair there, yelling at me. Okay, so 2 squared is 4, times 3 is 12, so 3 over -14. There we go. All right. X is greater than 0. F is a function such that this is the derivative, and then the second derivative, I guess we could have done this using the quotient rule, but they did it for us. How about that? Which of the following is true? Okay, so they're asking questions about decreasing and increasing in concavity. So I'm going to make sign charts for these. In fact, I'm going to make one sign chart. I don't know why it went down like that. It's supposed to be a straight line. And on the top, I'm going to put f prime, and on the bottom, I'm going to put f double prime. So let's see. Here, where is that equal to 0? So the derivative is natural log x over x. And natural log does not exist for numbers less than 0. So I'm just going to cap this at the end at 0. Not going to go below that. And where does this equal 0? Well, this equals 0 when natural log x, multiply that up there, equals 0. And that's e to the 0. That's at 1. So the first derivative changes sign at 1. And if you take the natural log of something less than 1, that's going to go from negative to positive. Like that, because I know what the natural log function looks like. It looks like this, right? And that's 1, negative to positive. All right, how about this? Well, f double prime rather, is going to be equal to 0 when this top part is equal to 0. So let's just set that top part, because this is always positive, right? And the bottom of a fraction can't change whether it's equal to 0 or not. So that's when natural log x is equal to 1. That's when x is equal to e. E is about almost 3, so I'll put that there. And then what does this look like? Well, if I plug in something less than e, like let's say I plug in how about e to the negative 1? Then e minus 1, that's going to be positive. This is going to go from positive to negative. Right? This is always positive. This is just a constant, and this is like the minus sign in front of this. It changes. It's going to flip that over. So where the natural log function goes from negative to positive, usually if you stick a negative sign in front of it, it's going to go from positive to negative. Okay, so let's see what we have here. Decreasing for x is greater than 1. Nope. That's a bust, right? It's increasing. F is decreasing for x is greater than 1. Nope. That's increasing. F is increasing for x is greater than 1. True. And the graph of f is concave down for x is greater than e. Oh, that looks like it's true, right? Because it's negative up here. F is increasing for x is greater than 1. And the graph of f is concave up for. No, that's wrong. But it'd be, I don't know, that's tricky to get those signs right, so that'd be a likely wrong choice. And I don't know what the heck this is. That's not right. Hard to get that. All right. Am I on track with numbers here? Yeah, I am. Didn't skip anything. Okay. If y is equal to the sine inverse of this, then the derivative, okay, so sine inverse, the derivative of sine inverse is 1 over the square root of 1 minus x squared. That's just a fact that you are supposed to know. But this one has a little bit of, looks like chain rule in it, right? Because that's a 5x. Okay, so what's the derivative of sine inverse of whatever? It's 1 over the square root of 1 minus, this is where the whatever goes, right? Because it's not sine inverse of x, it's sine inverse of that. And then times the derivative of what's inside. So 5 over the square root of 1 minus 25x. Number 18, got a graph of a derivative here. On which of the following intervals is f decreasing? Okay, well, if this is the graph of the derivative, then these are the sign. This is whether, if you want to know whether f is increasing or decreasing, f is increasing when its derivative is positive, and f is decreasing when its derivative is negative. So if you want to know where it's decreasing, that's where this is negative. So from 0 to 2 and from 4 to 6. Now, let me just point something out to you. I don't want to make you, I'm not in the business of trying to make you feel dumb. But I do want to point something out here. On which of the following intervals is f decreasing? If you're looking at this graph and going like, oh look, decreasing and decreasing, 0 to 1 and 3 to 5. Hey, I'm so clever. No, but look, anybody, you could show this to any Algebra 1 student and say, hey, where's this decreasing? And they're like, decreasing? That's a big word. And you're like, that just means going down. And you're like, and they go, oh, okay. Like, well, here it's going down, and then here it's going down. Like, nobody is ever going to ask you that question. Nobody's ever going to ask you, calculus student, to look at a graph and just see where it's going down. Like, where's this going down? Oh, it's going down here. There could be layers of interpretation, right? But nobody's just going to ask you, hey, where's this graph going down? It's going down right here. That's never going to happen. So this is the sucker answer. There's a sucker born every minute. You don't want to be that sucker. All right. I'm sorry if you picked that. I'm not trying to make you feel dumb. I'm just going to point out, like, that's going to happen again. You're going to see a question like that, and that answer choice is going to be there. Figure above shows the graph of f prime, the derivative of the function f, on the open interval from -7 to 7. It's an open interval. Okay? So that means there's not maximums and minimums at the ends. If it's a closed interval, then endpoints get involved. If f prime has 4 zeros, 1, 2, 3, 4. How many relative maxima? So we're looking for maximums. Not at the endpoints. If it was closed, then we would have to consider one at the endpoints. I'll come back to that and tell you where it would be. So a maximum happens when the derivative